Hi everyone, welcome back. I hope you had a nice winter break and you're feeling refreshed and ready to go for a new term. Sorry I can't be there today, but hopefully this video recording will suffice for the lesson. If you have any questions about any of the content today that we're going to go over, please message me on Teams. And when I do get into college this week, I will do a recap about the stuff that I've not been able to teach you in person. Okay? Just to remind you about what topics to revise for you synoptic, you've been told already before Christmas, but they're there on the side. So tectonics, EQ2 and EQ3, and then globalization and coasts is pretty much everything, including what we're starting in coasts today. Okay? So if you've not started your revision already, I would strongly urge you to start. Okay? Because there's quite a bit of content that could appear on your exam. Alright? So, inquiry question 3 is all to do with sea level change and how it's affecting our coastlines, so let's make a start. So today we're going to think about some longer term processes that have been affecting how our coastlines have changed over time. So one question to think about, just to get us in the mood, do sea levels change naturally, or is it just because of humans and global warming? Or is it a combination of both? Okay, so if we look back over geological time, all right, so we're on page 28 of your booklets. This graph isn't in there, so don't worry, okay, but you could write a note somewhere at the top. But if we look over geological time, all right, and through our rock record, we can see, and people have worked out that our sea level has changed over time, okay? So whenever we've got a graph, and there'll be lots of graphs today, always look at the axes, okay? So on the x-axis, we have geological time starting at 540 million years ago in the Cambrian, up until we're probably just like a pixel on this scale, okay? But most importantly is the y-axis here, the sea level change in meters, and we can see how it's changed dramatically over geological time, right? It's it's risen to about 250 meters at one point, okay? And it's also decreased over geological time. Now, this can be due to natural processes, okay? Humans weren't around at this point, so it must be a natural process. So what we've got is sea levels rising associated due to supercontinents like Pangaea breaking up, as well as creation of new lithosphere, which we'll go into later on. Okay. Over geological time, we have seen a dramatic change in our sea level. Going a bit more recent, so this is a graph of the past 500,000 years before present. So if you look at the x-axis again, present is here. On the other end, on the left hand side, we've got 500,000 years. And what we can see is how the global mean temperature is changing. Now, you might be thinking, what's this got to do with sea level? Well, just bear with me for a second, because this graph is pretty important. It's showing us that, well, over geological time, we have had these cycles of warming and cooling, okay? As indicated by these snowflakes, yep. So we've had periods where the mean temperature has been very cold, and then it's been quite warm. Now, this is the past 500,000 years, but if we look at another graph of 140,000 years before present, we can look at the sea level, and we can look at paleo data, so old data, and if we overlay the sort of peaks and patterns of the graphs, we get this, okay? Now, this is quite a crude thing, alright? All I did was mess around with this in PowerPoint. But hopefully you can see that where the red line is high, which is the temperature, there are high sea levels. And where it's low, there are low sea levels. So there does appear to be some sort of correlation between global mean temperature and the sea level. If we zoom in to a bit more recent geological time, so the past 10,000 years, what can we tell? So between 10,000 and 7,000 years before present, alright, we had this rapid increase in sea level. And that's been associated with the glacial ice melting, alright, from the last glacial period, as well as thermal expansion of water, which is a process that I'll talk about in more detail later on. Now, 10,000 years ago, the UK was a bit of a different place. This is a paleogeographical map of 10,000 years ago. And what it's showing is this landmass called Doggerland. Okay, so you've got this diagram on page 28 at the top. And you can see how as the glacial ice was melting, this land is disappearing because of the sea level rising. So at one point, Doggerland, which is this area here, is a piece of land that connected Britain to mainland Europe. And as glacial ice melted, sea levels rose, and we lost our connection, a physical geographical connection to mainland Europe. And archaeologists have found, remains of Neanderthals, and you can have a look at this link on Teams for a Guardian article. It's quite interesting. So that's what's been happening in the past 10,000 years. But let's go even, more recent. Let's focus on the past 2,000 years. So now this graph has changed. So we've got 0 AD here, all right? And then we've got 2000, so the present day is on the right-hand side. And what can we tell? Well, what geoscientists use are something called proxy measurements, okay? And these are measurements where it's not a direct measurement of sea level change, okay? But it's a measurement of something else which we can use to infer past sea level, okay? So it's a bit like when people are trying to work out past climates, all right? They will look at dendrochronology and tree rings measurements to look at growth of trees and seasonal changes, or they'll look at ice cores, okay? So a proxy measurement is just when we measure something else to infer the thing that we're interested in. In this case, it'll be a sea level. And what can we see? Well, between 0 and 1000 AD, the rate of sea level is pretty constant, okay? And then it starts to increase. And then you'll notice that, okay, between 1500 and 2000 years ago, we've seen this rapid increase. And when we study water and carbon cycle, we'll go into more details about what caused that, but you can pretty much have a guess. Yes, it's due to the Industrial Revolution. But on this graph as well, we've got 3 different sets of data. We've got proxy reconstructions, we've got observations, and we've got model data. Okay. Now, we didn't start measuring tidal data until 17th, 18th century, okay? But there we can see our direct measurements of the sea level, and we can see that's increasing over time. So if we zoom in a bit more, this is a slightly different graph to what you have, all right? But if you look on the right-hand side in your booklets, okay, you'll see that satellite data 1993 to present graph. This is basically a similar version of it. What can we tell? What are the key takeaway points? Well, it's increasing. Yep. This change in sea level compared to an average has increased over time. And one thing that I would, definitely write down is that this global sea level rise is accelerating. So it's more than doubled from 1.4 millimeters per year for most of the 20th century to 3.6 millimeters per year. Okay? And that's quite worrying, especially if you live on the coast. And that's what the focus is on this inquiry question. Okay? So while today we're going to focus on the long-term causes of sea level change, it's important to note that there's some short-term changes or short-term causes of sea level change as well. Now, you have some space in your booklets on page 28 to add some notes in here. It's not a lot of space, unfortunately. I do apologize. So if you want, you could write these in your exercise book, and then you could condense them later on into your booklets. There are some different causes of sea level change. The first one being tides. So if you've ever been to the coast, you'll see how the sea level will change throughout the day. Okay? And that is because of the tides. It's this regular rise and fall of sea level caused by the gravitational pull of the moon and the sun. And so if you've ever been on the coast, if it's quite a rocky coast, sometimes you've got to watch out for the tide, because if the tide comes in and you're on a wave-cut platform, you might be stranded. You might be in trouble. Okay? So if you are interested in doing a coastal NEA project, be wary of tides. There are 2 other short-term causes of sea level change. So we have low pressure systems, which you should be familiar with from GCSE when you studied about tropical storms and hurricanes. This is where water is drawn upwards during a hurricane or a low pressure system, and that's where you get a storm surge. And we'll cover storm surges in a bit more detail in a future lesson. Okay? So don't worry about if you can't remember what a storm surge is at this point. We will come back to it. And the third one is strong winds. So if you've got very strong winds, this can cause water to be pushed onto a coastline, say at a pier. So you may have seen pictures of this happening, say if it's very stormy in Blackpool. And this can lead to localized changes in sea level. Now, note here the use of that localized changes in sea level. That's an important geographical lens to evaluate. So it might be that some of these causes are only going to affect certain areas. So strong winds might only affect Blackpool. It's not necessarily going to affect Norfolk, for instance. So just be mindful when we're going through stuff. How could I evaluate these things? Yeah? How can I look at these through a geographical lens of scale or place? Now, onto some longer term changes. Now, there are going to be two new words to introduce you today: eustatic and isostatic changes. So you'll have some space on the bottom of page 28. On page 28 at the bottom, you've got some space for eustatic changes. It says are due to. Don't worry about finishing the sentence. For now, you could just put in this definition here. So a eustatic change is a global alteration. So note the scale here. It's a global change in sea levels caused by changes in the volume of water in the oceans or the size of the ocean basins, typically due to climate factors. So essentially, we have a change in sea level caused by the amount of water in the oceans changing. Or, we'll come back to this in a bit, the size of the ocean's basins changing, okay, due to tectonics. Now, going back to our interglacial and glacial periods. So during colder glacial periods, you're going to have more water on a global scale stored as ice. And that could be as an ice cap floating on the sea, or it could be continental glacial ice. So this is a diagram of the water cycle. All right, it's quite a simplistic one. And essentially, when we've got colder glacial periods, we're going to have more water stored in ice. What's going to happen to the sea level if we've got more water stored in the ice? The sea level will decrease, okay? Because there's only a fixed amount of water on the planet. So we're not going to have glacial periods all the time. We're currently in an interglacial period. And so what happens in a interglacial period? Well, we have continental ice sheets melting. And so we've got water going back into the oceans. Okay? And as you've probably worked out, this would result in a global sea level rise. The key takeaway points from this: so eustatic changes are due to changes in the volume of water in the oceans or the size of the ocean basins. It's a global change in sea levels, and it's typically due to climate factors. So when it's colder, when we're in a glacial period, we'll have lower sea levels. When we're in a warmer interglacial period like we are now, sea levels will rise. Just as a side note, not all ice is equal in terms of contributing to sea level change. So I'm going to quickly go through this. It's not in the booklets, but it is an important thing to note. Now, there are some videos and links to videos on the sides, so feel free to take a look at them. Maybe I'll show them to you when I get in. Now, what is this? Well, this is a model of some sea ice floating in the ocean, okay? It's a bit blurry, but hopefully you can see the ice cubes and they're floating. And the question to you is, what do you think will happen to the sea level indicated by the black line if the ice melts? So will the sea level rise, fall, or stay the same? Take a few moments to think what's going to happen. When all this ice melts, which is floating, is the sea level going to rise, fall, or stay the same? And we know that the current sea level is indicated by that black mark there. So if you said that the sea level is going to increase, unfortunately that's not correct. What actually happens is the sea level is going to remain the same, which is quite an interesting observation. Now why this is something to do with the Archimedes principle, which is some physics I'm not going to bore you about. Okay, so it's there on the side. But, think about on a global scale. If we have some ice caps that are on the sea, so icebergs, right, that are melting, it's not going to contribute a lot to sea level change. So let's have a look at another model. Now this time, in my model, I've got some crust, all right, indicated by this rock. I've got a sea level, and then I've got some ice on top. And again, I've got the sea level here. So what do you think is going to happen this time? Is the sea level going to rise, fall, or stay the same? So this time, the sea level's risen. So what we need to be worrying about is the melting of continental ice. That is going to contribute to our eustatic sea level changes. This is a table showing the equivalent water depth if these stores of water were released. And essentially the takeaway from this is that if we melt all the frozen water, the sea level would increase by about 65 meters. Now, if all the water from Antarctica melts, that's 57 meters. But if Greenland melts, it's only 7 meters. Okay? So there's an 8 times difference between the continental ice just in Antarctica, right? And Greenland. And then you've got, in the others, you've got places like Switzerland and New Zealand glaciers. So it's that Antarctica ice that we need to be watching out for. Now, another process is isostatic changes to sea level. And this is due to the Earth's crust moving. And if you remember back from our tectonic stuff, we had our different models of the Earth. And you should recall that the lithosphere is rigid and the crust is part of the lithosphere. But underneath the lithosphere is the asthenosphere, which is ductile. Okay? So what happens is you have something that's quite heavy. So in this case, the glacial ice sitting on top of the crust. And the crust is being pushed down into the asthenosphere. Now, isostatic changes occur locally, but it's very slow. So at the minute, it's about 0.1 millimeters per year at Blackpool. So Blackpool is rising about 0.1 millimeters per year. Okay? And essentially the key takeaway from this is during glacial periods, the weight of the ice makes the land sink. And we call that isostatic subsidence. So subsidence is when something is sinking. So if you've got building subsidence, it's when a building is sinking into the ground. Okay? In this case, when we've got a glacial period, where there's an ice sheet, the land will sink, or the crust will sink into the mantle. Picture B is showing what happens during an interglacial period. So the glacial ice has melted, and that's quite rapid, but as the ice begins to melt, you've got a reduction in the weight, and the land starts to readjust and rise, and we call that isostatic recovery. So essentially, areas where there were glaciers, and the glaciers have melted, the land is starting to rise up. And picture C is a sort of equilibrium. Okay, so that's when the crust is balanced with the mantle. Now, if we have a look at a map of Scandinavia, let's try and think about what's happening here. So these ISO lines are showing the rate of uplift in millimeters per year. Again, when we're looking at a map, there's no key here, but let's pretend that this is the key down here. What can we tell? Well, up here in the north of the Gulf of Bothnia, we've got a rate of uplift of 9 millimeters per year. That's quite significant. That's nearly a centimetre per year. Yep. If you factor in, in a century, okay, that's going to be a meter, okay, of uplift. Just under a meter, 90 centimeters. Yeah. However, in the south, near Denmark, Copenhagen, or Lithuania, we've got a negative rate of uplift. So here, the land is sinking. Now, you might be thinking, well, this is due to the north being glaciated. And you'd be right. We can tell that, well, where we have these big rates of uplift, this is where the most of the ice sheet would have been. All right, the bulk of the weight of the glacier would be up in the north because that's where we're having the highest rate of uplift. Now, if I was at college, I would have given you a sheet with this on and asked you to annotate it, but unfortunately I'm not there. So what I'll do next time as a starter, we'll go through this and we'll annotate it, so don't worry about writing too much down now. But maybe later on, when you scan the QR code for the tasks, you can look back at this and go through it. Essentially, it's a model showing you what happens in the lithosphere and the asthenosphere when you've got an ice sheet, okay? So we have the weight of the ice sheet pushing down on the crust, which is pushing down on the asthenosphere, okay? And the asthenosphere is ductile, and it's flowing away from where the weight is acting on the crust. So this is all, it's what we call mantle dynamics, okay? So remember, the mantle, the asthenosphere, part of it is mobile, especially the asthenosphere. So we've got the weight of the ice sheet pushing down on the asthenosphere, and that's pushing the asthenosphere away, okay? So we've got this bulk of material being pushed away. And it's got to go somewhere. So where's it going? Well, it goes to either side of the ice sheet. So the material flows away and around the ice sheet, and it creates what are called fault bulges. And these are areas of uplifted land. So where we've got an ice sheet, the land is sinking. So we've got isostatic subsidence. And where there are no ice sheets, but either side of it, we've got this fault bulge uplift or isostatic uplift. Now, the ice sheet melts, okay, and that's going to remove that weight acting on the crust and lithosphere. So once the ice sheet is removed, the forces are no longer in equilibrium. So the mantle and the asthenosphere, they're going to react. So that mantle material that was previously displaced is going to go back to where it came from. And as a consequence, the fault bulges will begin to sink. And the crust under where there was a depression, where there was a subsidence, will rise. So that was eustatic and isostatic changes. Okay? So eustatic changes are due to change in sea level due to the amount of water present in our oceans. And then isostatic changes are due to the changes in the land level, okay? So the land level is increasing or decreasing depending on whether there are glaciers or not. But there are other factors involved with longer term sea level change. So we have thermal expansion, seafloor spreading rates, earthquakes, accretion, ground subsidence, and thermohaline circulation. Okay, and some of these are going to be affected by humans, such as perhaps accretion, ground subsidence, perhaps thermohaline circulation due to climate change. Okay, and we'll be revisiting some of these when we look at water. For now, okay, on page 29, you have some boxes, okay, to take down some notes. Don't worry about that explaining isostatic changes around the UK question. We'll come back to that at the end when you've got in your independent work. For now, we're just going to add some factors in these boxes. Okay, thermal expansion. Essentially, when ocean water warms, it expands in volume. So you get a rise in sea level. Now, this is quite a concern because it's a significant driver of global sea level rise. So I've got a graph here which is showing how if we just added water, right, from glaciers, this is the sea level rise we would get. But when you factor in the thermal expansion that goes along with climate change and global warming, then you have an additional increase. So it's a combination of effects that is leading to this increase in global sea level rise. All right. It's not just isostatic and eustatic changes, but it's also this thermal expansion of water as it heats up. As the temperature increases due to climate change and global warming, seawater will expand in volume and you'll get a rise in sea level. Another factor would be seafloor spreading. Now, when you have faster seafloor spreading, you have a reduction in the ocean basin volume, and this causes sea levels to rise. Whereas if you've got a slower spreading, this leads to a sea level fall. Now, you have to imagine this. So here we are at a mid-ocean ridge. Okay. Now, imagine for a second that if we had a fast seafloor spreading rate, well, what would happen is at this mid-ocean ridge, which is where we've got basically an underwater mountain range, okay? If you have rapid seafloor spreading, this mid-ocean ridge grows in height. And it's going to push that water upwards with it. So when you have a faster seafloor spreading, it displaces the water by increasing the height of this mid-ocean ridge, and that leads to a reduction in the ocean basin volume. So to summarize, faster seafloor spreading leads to a reduction in ocean basin volume and a sea level rise. Earthquakes. Now, you can see here just from this picture the before and after of an earthquake and see how it's had a significant impact on the coastline. So in the 2004 Indian Ocean tsunami, there was some parts of the crust which were displaced as much as 15 meters vertically. Okay, so the crust has risen by 15 meters. Okay, and that could cause tsunamis, but it can also permanently change the crust so that there will be that permanent change in the coastline. So the earthquake also caused some parts of the city to sink, leading to a permanent flooding of that city. And you can sort of see it here in the photo. So in the before, you've got all these fields in the middle, presumably where they're growing crops, rice perhaps. But then in after, they're completely submerged. Okay. And the raising of the seabed, which triggered the tsunami, reduced the capacity of the entire Indian Ocean. So you've got that permanent rise in sea level. Now it's only around 0.1 millimeters, which might not be a lot, okay? But consider that what we spoke about in tectonics, where earthquakes are happening all the time. So it could be that, yes, you might have only 0.1 millimeters of sea level change, but consider the frequency of earthquakes. Okay. So accretion is a term that we have used before, but it might be one that you've forgotten about. It is the accumulation of sediment or material in a coastal or riverine environment. Okay, so a river environment. And accretion can raise land levels. Okay. This can actually cause a reduction in local sea level rise and reduce flood risk in specific areas. If you're having that built up or the buildup of material, then you will have a increase in land level. Therefore, you will have that flood risk reduction because the sea level is getting relatively lower to the land. However, if you've got a lot of sediment accumulating, the weight of that sediment can cause the crust to sink and cause relative sea levels to rise. And this is what's happening in the Thames estuary in the southeast of England. So this is a photograph, it's a satellite image rather, of the Thames estuary, and it you can see that estuary is there's quite a lot of sediment, okay, and we've had all that sediment being built up over there, causing a sinking of the crust. Subsidence, okay, of the land has many causes, okay, it can be natural, but most of the time it's due to human processes. So ground subsidence is caused by things like groundwater extraction, mining, a natural compaction of sediments, but it lowers the land surface, okay? And this leads to a relative increase in sea levels and an increase in the vulnerability to flooding. This is another satellite image, but this time of Jakarta. And again, if we look at the key, we've got a bit of a color path going on. All it's showing is the land subsidence rates. Okay, in that, well, it's not a rate, it's a measurement. So it's showing the land subsidence during the period of 1974 to 2010. And we can see that in the north, okay, on the coast, we've had subsidence of 4.1 meters, okay? And some parts are sinking by up to 25 centimeters per year. And this is due to excessive groundwater extraction, urbanization, and the compressibility of the soil. When you start building on that, consider that urbanization, all those towers and roads and infrastructure being built is quite heavy, right? It's gonna compress, it's gonna start sinking into the ground, okay, due to the weight. So unfortunately in Jakarta, and we will come back to Jakarta, it's unfortunately a place experiencing extreme subsidence as a consequence mostly of urbanization and groundwater extraction, both human actions. This next one, thermal haline circulation, is something that we will return to in water as well. But essentially what happens is we've got a conveyor belt, okay, in our oceans that moves water around the globe, okay? And so the big concern with thermal haline circulation is a weakening of the North Atlantic, okay? So due to melting ice of the Arctic, what we have is the seawater is becoming less salty, which means it's becoming less dense. And this is a problem because you want cold, salty water to sink up here to drive this conveyor belt. Okay, it pushes it around. Now, what's happened to this is that the thermal haline circulation is slowing down, and that's having some consequences. So, thermal haline circulation is a really important global system because it redistributes heat and water mass, and it affects regional sea levels. Okay, that's an important thing. It's regional sea levels. At some point, I'll show you a clip about how cities in the east coast of North America, like New York, are experiencing rapid sea level increases as a consequence of this. So, like I said, the Atlantic part of this global current is concerning. So it has a name, the Atlantic Meridional Overturning Circulation, or AMOC. And if this weakens, well, it is weakening, it is contributing to sea level rise across North America. So when we're evaluating these things and these factors involved in sea level change, this is a good one to, evaluate, in that it's only going to affect certain regions. Okay, it's not a global factor, it's only regional, but it's still pretty bad. All right. And the one thing with AMOC, there's a lot of research that goes into it because it's a massive concern. We talk about uncertainties and predicting the future. It's like Still working on this. Still unsure on, how big of an impact it will have on not necessarily a regional scale, but on a global scale. So this is a little poster, and it's showing how there are different parts of these circulating currents, okay? And some parts will be affected more than others. So this purple part, this abyssal layer, this bottom layer, that is growing in volume, which is pushing up everything else. Now, I mentioned about relative sea level before, and what you need to think about with relative sea level, and you've got some space on page 29 for this, is that it's the result of all factors, okay? So relative sea level change takes into account eustatic and isostatic changes, okay? Because you might have parts of the world where there is isostatic uplift, okay, like in northern Scotland, as this map indicates. So even in the north of England to an extent, we have isostatic uplift, okay? Now it might be that this uplift is causing the land to increase at a greater rate than eustatic changes, okay? So in that case, in Scotland, we might not see coastal flooding as much. But then in places like in London and the southeast, where the land is sinking, okay, we've got isostatic subsidence, and combined with the fact of increasing eustatic changes, it might be that, okay, in the southeast, that's where we're going to have some serious problems. So on a UK scale, again, certain factors will contribute more to sea level change in different parts of the country, okay? So sea level change is not the same everywhere in the world. Some places are going to be fine, others not so much. So in the UK, the concern would be in the south. This is quite a cool website to go on. It shows you a prediction of what the sea level change is going to be based on different scenarios. And there's a little video to watch in your own time. Now, this is quite, it's quite a nice thing for news outlets to do from time to time. Essentially, when there's a new paper with different scenarios, they like to make their own graphics, and this is one where we've got a possible 2-meter rise in sea levels, okay? So what it's showing is that, fine, certain areas are going to be affected more, okay? So this North Norfolk, for instance, where Hull is, Humberside, all right? But certainly parts of, Wales and Cornwall, perhaps where they've got rocky coastlines, not necessarily going to be a big factor or a worry. However, what they like to do is, some scare tactics and look at some extreme scenarios of 84 meters, and yeah, that would be an interesting situation, but very unlikely. Now, if this was to happen, I think Rochdale might become a new seaside resort, maybe. But certainly on a global scale, certain parts of the world are experiencing sea level change at a faster rate than others, okay? Such as Indonesia, all right? East Coast there, okay? This is a slide showing different outputs of a model, showing how the UK coastline would change if there was a 30, 50, or 100 centimeter rise in sea level. Different models will behave differently, okay? So, take them with a pinch of salt. However, it is interesting to note that certain areas of the UK will be affected more, regardless of which model you use, okay? So certainly, in the East Midlands or Norfolk, look at where Cambridge is, that area seems to be affected considerably. That and Hull and Humberside, okay? So certainly in a UK context, relative sea level change will impact certain places more than others. And that's a combination of, everything we've talked about today, okay? So isostatic and eustatic changes, but perhaps even, things like mass wasting, the geology of an area. So, if you have any questions about anything I've talked about, please message me on Teams. This recording will be on YouTube, okay? I'll send the link out afterwards, so if you want to rewatch it anytime, feel free. Here are a list of tasks for you to be getting on with for today, okay? Enjoy. If you've got any questions, please message me and I'll get back to you as soon as possible.